Thank you. I have 3 comments before I start my talk. The first is to thank the organizers very much for this very interesting workshop. I enjoy being here very much, and I look forward to the coming days as well. My second comment was relating to Dennis mentioned that there was a misprint in the program saying that Frank is from Stockholm University. I wish it was not a misprint. That was my second comment. Thirdly, I'm a little bit confused what to talk about because Dennis said starting this session that now comes a session on new results, and just before that Phil approached me saying I made some progress on the joint stuff you are talking about in this talk that I read the abstract of. That's not confusing. The confusing bit is that I didn't know what abstract he was talking about, and I have no new results except what Phil did this morning. So I think the explanation to that was that at the time when I was invited, probably I sent in an abstract, but then later on I was kindly but firmly ordered by Hans to talk about something different, and maybe the old abstract still remains. I don't know. Anyway, I will not talk about my own work at all. I will focus on what things could be solved in the future. That's my plan. Let's see if I can. First, some excuses. So I will mainly focus on SIR epidemics. Of course, what I will talk about is biased towards my own interest. And I want to emphasize what Frank already said, that the focus of what I and Frank are talking about is stochastic models. That doesn't mean other models have less value. It's only, at least from my point of view, my knowledge is in probability, so that's why I'm doing stochastic models. All right. So the way we divided this talk was that Frank should talk about the early stages, and I should talk about what happens. Where could stochastic models be useful even after the early stages? So one such situation is where you have small local structures. We have heard that several times, so I thought I'd more or less skip that. Of course, if you have uniform mixing, where's the pointer? Okay. If you have uniform mixing, you know that the final size solves this type of equation, so there is no deterministic models are perfectly useful then. Whereas if you have smaller local structures, randomness really comes into play, which has been illustrated by many people even before the previous workshop. And the reason is that what happens in the household, because it's small, really is random. How about another example where stochasticity matters even in a large population for the final size is if you have networks. We've heard quite a lot of networks. So here the network is supposed to mimic some type of social structure in the community. This one is, as you see, a static network. And then you can have an epidemic evolving on this static network. The simplest one is, which we've heard in several talks, is where you, so if this is me, if I get infected, I would get infected by one of them, and I have a chance of transmitting it to the other one with a probability p, and these are independent events. And the final size for such a model, as far as I know, cannot be derived unless you look at the actual degree distribution. So I don't think there is any mean field result for the final size. I might be wrong, but there it really matters the degree distribution. Not only the mean and the variance in the degree distribution, but the whole distribution. So if we have local structures, even in a finite and fixed population, the final size really depends on on stochastic models, or it should be analyzed using stochastic models. But there are a lot of open problems in this area as well. For instance, we've heard some talk about this, but spatial models seem to be much harder to analyze. So whenever you have some local structure and also space, I think there's much less done there. Also, models where things change as the epidemic evolves could be due to different reasons. I thought maybe this is an old version of the talk. I hope it's not. So either that people change behavior because they realize that something is going on, but it could also be that the infectious agent evolves over time, so maybe it becomes more adapts and spreads better after a while or something like that. Of course, in estimation, but also network models, I think there's need for network models where you have different types of nodes, different type of individuals, but also different type of edges reflecting close friends and distant friends maybe, or a continuum of friendships. I think there's more work to be done there. I think Frank did not mention this, but there's an old conjecture in this paper which has been cited many times during this workshop, and which says that what is the best way to immunize or vaccinate? And the conjecture is that one should reduce. You should vaccinate in the large households, but not everyone, but such that you reduce the number of susceptibles to some level. That's just a conjecture in general, and to prove this, I don't know if it has all that. If it's all that interesting from an applied point of view, because maybe people already believe it's true, but it's nice to have a proof of it, I think. So these are some open problems for the situation where we have a fixed community and the epidemic evolves, and even final sizes, the simplest situation, final sizes using stochastic, where stochastic model seems to be the way forward, but there are a lot of unsolved problems. And then, so this was maybe I forgot to say that if you have a fixed community, large fixed community, of course that can only be the case if you have a very short-term outbreak. But if you look at in a longer time perspectives, you cannot approximate the model to be fixed. So you would have a population that evolves in time, and then well, I probably have that slide. So if you look at the deterministic curve, which didn't come out that well in this slide, so this is a problem which Odo mentioned to me. So if you look at the deterministic curve, it looks like maybe that illustration was not so good. So the first trough goes down quite a lot more than the other ones. So this is the deterministic curve, but if you have a stochastic model, you know that what happens here can be analyzed using branching processes. That's what Frank talked about. But then so it could die out, or else it takes off, and if you have a stochastic curve, it probably goes down like this. But then the question is, due to randomness, what's the probability that the epidemic goes extinct in the first trough here? If it doesn't, it will probably reach stationarity, and then after a very long time it will probably go extinct, or it will go extinct. So did I miss out something? Yes, so this is the model where you have influx of new people, but you have a sort of a steady state population size. So this here, here we have I of t, and this is the endemic level, which is the average population size multiplied by some steady state solution to the differential equations.
But also n has to be fixed to make this problem interesting. I mean, a finite n.
Yes, finite but large n. I will later talk about the growing population. But so if you have a population which fluctuates around some equilibrium value, then this type of question is interesting. So this part is solved using branching process. How to compute the probability of going extinct in the first trough as a function of this value n, the average population size, and model parameters. I don't think there are very few attempts to solve that even, and I don't think there are any satisfactory solutions as far as I know anyway. And then, well, probably that will come later. So what's the chance of the epidemic going extinct in the first trough? That's a problem maybe of academic interest, but also of from a more empirical point of view perhaps. And even for the very simplest model, the SIR model, where you have maybe constant immigration of people and they die after exponential times, I think this is not well solved. And if you do reach this equilibrium or the endemic level, if n is finite, so if the population fluctuates around some value, it's known that eventually the epidemic or the disease will go extinct. Well, in fact, not only the disease, but the community will go extinct as well. But this might happen after a very long time if n is large. But one interesting question is how long will this take? And this is closely related to what was mentioned yesterday, I think, the critical community size, and that's defined in different ways. You can define it different ways, but more or less it's saying that if the time to extinction is very large, then we're above the critical community size, whereas if the time to extinction is short, then we are below the critical community size. So these two questions are intimately related. Yes, so here there has been some work. For instance, Ingmar Nocell has written several papers on this, but also others. So how does the time to extinction depend on the different parameters of the model? And I think more work could be done there, but perhaps moving to towards reality, the results rely on n being large, and I think in reality, the larger communities you look at, the less likely is the assumption of uniform mixing satisfactory. So as n grows, you should probably look at sort of subpopulations, and to study this is I think quite important work. So this I have written this in a few places. It means that I didn't do the literature search. So if you've done some work here, it means that I didn't forget you, or I never knew of it, perhaps. So what's this? Okay, it's always nice to get some surprises during the talk. Yeah, okay, so here is a simple model where you can make progress. So the simplest model that you would define is, suppose that individuals are born at a constant rate n, so n will be the population size around which, the population size will fluctuate around n, and you die at rate 1, not very realistic, but I'm not the only one making these simplifications. And then if you get infected, you recover at the rate gamma, and during your infectious period you infect others at rate lambda. So let's see why I wrote down this. Yeah, okay. So then you have this set of differential equations. This is actually exactly this model here. Then it's easy to solve that. The endemic state is solved by this. Eventually, the deterministic system will end up here. So this I hat is exactly what you have there. Yeah, okay, so I'm just repeating what I said previously. So the question is, how does the time to extinction depend on these model parameters? That's not well known yet. But you can make some... yeah, there's much less done. Okay, so this is for the simplest case. Now I realize what this was example was. This was for uniform mixing, and there's some work done there, in particular by Ingmar Nocell, but also others. But then, as soon as you put a bit of structure into this type of model, there's the work. It's much harder, and there's much less work. There are some. Martina talked about this earlier. So there are models for these networks, how they could evolve in time, but there is very little analytical work there on dynamic networks, but also even less so on epidemics spreading on such dynamic networks. And I think this is an interesting problem that deserves more attention. And the thing is that if you have a network evolving over time, to describe the endemic level is very hard, even if you think, because it's not only one number. Of course, there will be an average fraction infectious at any given time, but how are the infected people spread in these local structures? That's probably very hard to describe even. An alternative, maybe relating to what Paolo said, you could have a population size fluctuating around some value n, but an alternative would be to have a population which grows exponentially. I guess the human population has grown exponentially, so maybe that's a better approximation. And then you can actually have not only quasi-stationary distributions, but you could have stationary distributions in terms of proportions of the community size. So a model for such, a very simple network model, which I've looked a little bit, is the following. So it's the simplest network model we could come up with. So there the population is modeled by individuals give birth at rate nu and they die at rate mu. So it's a birth and death process. The population is a birth and death process. You give birth at the rate nu, which is larger than your death rate. So that means that the population will grow exponentially. How do you model the network on this population? Well, first you say that newborn have no edges, and during your life you create new edges at rate alpha, and each time you want to create an edge, you pick one uniformly in the whole community. That's the simplest model you can think of. And sometimes your friendships disappear. So at the rate beta, each friendship disappears. So that would be those two. This would define a network model in a growing population. You can study that. Even that is quite hard. And then you can make it even harder by, let's assume that this network has grown for a while, and then you infect one person in that network. And the epidemic model works such that while you're infectious, you infect each of your friends at rate lambda, and you recover at rate gamma. So what can happen with such a model? Just to remind you, there are 6 parameters, 2 population parameters, 2 network parameters, and 2 epidemic parameters. So birth rate, death rate, creation of edges, or dissolving of edges, infection rate, and recovery rate. what could happen without such a model. There is some work trying to describe how the network will look after a long time. You can compute the degree distribution of individuals in the sort of stationary phase, and compute the degree correlation. There will be a positive degree correlation, but unfortunately there will be no clustering, which we know there is in all the human true networks. So this simple model, which is very hard to analyze, needs to be made more realistic later on, I think. And then if you analyze this epidemic going on here, Peter and I have been trying to do that. The first, well, this is all what's here is conjectures, because I don't think there's formal proofs to anything. But there seems to be three regimes. One is, depending on the parameter values, one is that you're below threshold, so you infect one individual in this large growing community and it will die out immediately. The second regime, depending on the parameter values, is that you infect one individual, it could either die out or it can take off, but the rate at which it takes off is slower than the rate at which the population grows. So you will have an infinite epidemic, but the fraction is still very small. Or the third scenario, which is the one that's hardest to analyze and trying to describe, that you have an initial, it takes off and it grows quicker than the community size, but then trying to describe what happens. Probably there is an endemic equilibrium, but trying to describe this it seems very hard. So to analyze these type of models and maybe more realistic models is a problem, a very, at least to my taste, very interesting problem, but unfortunately it's quite hard. And you could do the same thing if that was for a dynamic network, but maybe you should also, maybe it's more important to look at the dynamic household model. So households grow and disappear and are split because someone moves, and trying to analyze how such an epidemic, what happens if with that type of household model, and also if you introduce a disease there. That's interesting, I think. Yeah. Spatial epidemics, we've heard much about that. It's very hard. They are very hard. But still, that doesn't mean that one shouldn't work on them. So I think there's more to be done, definitely more to be done there. Yeah. So Dennis gave me the sign that I should stop soon, so I'll try to do that. What's here? Yeah, so maybe, did I hear? Yeah, okay, so also models where things change over time. I addressed this earlier. I think there's much more work to be done there. Of course, not only stochastic, but here also deterministic models are very useful, I think. Perhaps a bit more useful in the beginning, at least. Critical models, maybe that sometimes I think, why does anyone work on critical models at all unless you're interested in the theory? But one sort of defense for that would be that if you have a continuous vaccination of the community, if this vaccination fraction drops, you will eventually start seeing smaller outbreaks, and that's in the situation where you are at criticality. So that is one defense for analyzing critical epidemics, where the effective reproduction number is around 1. So this is my last slide, and here I've tried to summarize some important problems. Let's see if I can read through them very quickly. So these are from Frank's part, more realistic, mathematically tractable models, and looking at this real-time growth rate, which Frank discussed, and also the interpretation between the finite population interpretation, which Frank talked about, for branching process. I think more needs to be done about things varying. Here I have this genetic evolution. Maybe we didn't talk about that, but I think more should be done for evolving infectious agents, spatial epidemics, this extinction in the first trough, and the endemic state in dynamic populations with local structures. Okay, that's it.
Questions? Maybe first, if there's anything very specifically for Tom, but if Frank would like to maybe come up with
maybe
again, then you can do a double. I should thank you for doing such a good double act of the talks dovetailing so nicely together. So it seems appropriate to have Frank up for the question.
Yeah, I agree.
But Ingmar, you have.
I have a comment on the figure that Tom drew by hand on the blackboard there. I assume this, of course, refers to an SIR model with demography.
Yes.
And it does not involve any network structure. I would draw that figure differently. I would interpret your drawing as saying that the infected number of individuals proceeds like a damped oscillation. But this is fundamental, and I think it goes back to descriptions or hypotheses by Bartlett in 1956, where he claims that the kind of stochastic model would explain recurrence of outbreaks without damping, and that is the major difference between what I claim here and what you drew. Okay. And on this question, there is a beautiful paper that maybe all of you have not seen that was published in 2007, with authors are Rachel
Cask. Cask, is it?
I remember her first name, and Cindy Greenwood, and they prove for exactly this model that recurrence without damping does occur in the fully stochastic model. And this is a beautiful paper, and I recommend its reading to everybody who is interested in these things.
Okay. So you're much more knowledgeable than I am. So my escape is that I erased the figure and now only kept the first trough. So that's the question I want to allude here. But you're probably right. But the rest was not the focus of. It's in the first trough that I was in.
But it also means that this question about the probability of absorption at the first trough would it is not so very interesting to look at only that thing. Because
okay, then you should. Yeah. Okay. All right.
I believe so.
Okay.
Yeah, but may I say a comment? So. It's of course you're saying that it's interesting to look at the stationary state, but the problem that you're referring to, that this
so could you speak a bit louder, maybe?
Yeah, this extinction in the first trough. It's really this problem is really not solved, not by physicists, I think, and it's really interesting. And then maybe also from a physicist point of view, this field of adaptive dynamics, it's the golden age of this field has passed maybe 10 years ago. At least for a physicist, it's now. Very hard to find a problem which would be really interesting, maybe some kind of application, but not in terms, of course, of exact results for adaptive dynamics.
Questions?
Maybe a comment more than a question. So you mentioned the equalizing strategy. It has been mentioned in various occasions. So I just wanted...
I forgot to call it the equalizing strategy. That may be a better description of it. I call it top to bottom, but equalizing strategy is what it should be.
The vaccination in households. Yeah. So I just wanted to point out that first of all, it has been looked at only in the context where the infectivity in households does not depend on the household size, while in reality we have seen the situation. Data suggests the situation is a lot more complex than that. And data is also contradictory. Different studies suggest different things, so it's not always obvious. The second point I wanted to make is that it looks a rather theoretical result, but it's not necessarily always that far from real life. This is a comment that Thomas House made originally, I think. when you have when you're thinking about vaccinating children, for example, then effectively you're reducing the number of susceptibles in every household to 2 if you think that the households are made up of 2 parents and the rest is made up of children. So it's a slightly different problem. You're not saying I have a constant amount of vaccine and I have to choose how to deliver it, because you assume you can vaccinate everybody you want and you just decide to vaccinate all the children. But there is an added benefit in vaccinating all the children to the fact that children may be more susceptible and more infectious, and the added benefit is that it's kind of closer to the equalizing strategy.
Okay. So you said the one with dynamical households, there was a Monte Carlo big agent-based simulation published in Epidemics by the group in Melbourne.
By the group in
The group in Melbourne. There's a big collaboration now.
Melbourne.
Yeah, so it's a big discrete time Monte Carlo based on real data. And you actually see the opposite of this. It's interesting because you generate exactly 2 people, for childhood diseases with no vaccination, you generate a pattern where exactly the 2 adults in the household have pre-existing immunity because they acquired it as children, and you've actually got a completely disoptimal set of all these kids who are still susceptible in with naturally acquired immunity. So I think that would be really great if there's some analytic, but goodness knows how, but the phenomena are very interesting, I think.
More questions?
Do you have a conjecture on when your dynamic network becomes in some sense like homogeneous mixing?
Comes like what? I did.
Homogeneous mixing.
It depends on becomes like homogeneous mixing in what aspect. I think in some aspects as soon as you have or beside the local structure have infections sort of uniformly, in some aspects you already then, even if it's very small, you're close to uniform mixing in the sense that you have this small world. So yeah, in some sense it's very closely related to uniform mixing, but still you would have clustering of infected individuals in these local structures. So sort of it depends on what question you're asking, in what respect.
If you translate that into when is it that you get persistent differentials from a network model that you wouldn't expect as much with a non-network model or homogeneous mixing, if you have persistent clusters that are driven by homophily, so within group mixing, and then differential behavior within those groups, you can sustain persistent differentials even though there continues to be some interaction between the groups. Right? So that's going to be different than a homogeneous mixing model, and that will persist throughout the epidemic. I mean, that would persist even in a dynamic network as new entrants come in or out.
It was just a remark on the question which was just posed. Of course, if the edges change at a tremendous speed, then you come close to homogeneous mixing. If they dissolve and are formed again at a speed which is light year, or which is really way faster than the rest of the dynamics.
I guess also meta-population model. So if you have like 10 cities, you have high mixing within, or mixing within the cities, but as soon as you don't need to put much mixing between the cities. If you just put above some value, of course, but not very much, then it looks very much like uniform mixing. So
You have persistent differentials in activity levels between the different units.
so I can't. Anyway, that's my impression in the situations I've looked at.
Excuse me, I did not hear what Martina said, and I think it was relevant to the comment that I made, but it's difficult since I did not. Could you repeat her? Can you?
Repeat. It's better that Martina repeats what she said.
But you won't hear it if I repeat it.
You better tell them off.
Maybe we talk about it afterwards.
Yeah. But are there any other?
Still, I did hear that you talked about persistence as well as
Persistent
recurrence.
differentials.
No, differential, different thing.
It is different.
Yeah.
Okay.
So it seems you have like additional heterogeneity
Right, so you have different groups that are defined by two things. One is assortative mixing by group, and the other is differential activity levels between groups. Then vital dynamics, that is births and deaths in the population, will not eliminate persistent differentials in disease prevalence. And neither will some activity that is, so it doesn't have to be perfect assortative mixing. They never mix with others.
Any more questions?
Maybe just ask about, since both of you insisted much on having realistic mathematically tractable models that include some kind of cluster or anything, do you have any suggestions of idea of what it could be?
But not really, no. No, I think all the ones I know have at some level there'll be a branching process. And Peter may correct me, but that's unless you go to sort of some percolation models, I guess.
Yeah,
they have a very rigid structure, which I don't think.
In percolation models, you cannot compute things.
No.
So, yeah, I agree. In branching processes, you can still can get numbers out of it.
Do you think, for instance, that the individual-based models that are around, are they sufficiently realistic in a sense? Because many of the big
agent-based models.
yes, one of the big ones.
I mean, why? Yeah, I mean.
Take anyone.
So one
American cities or something like that.
So I think they have they bring a lot of new knowledge. But so one scary bit about them is that there are loads of parameters that are given some values, and to me it seems, how do you know that these values are correct, and would things change dramatically if the combination of the values were changed slightly or something? That's a risk with them, but I think they definitely contribute. I mean, in real world problems, I think they are very important.
Maybe we should call the end to another long day there. Just quick announcements. First of all, if the organisers could meet just outside here for 10 minutes after this. But for everyone else, your next engagement, just remind you that we have now filled the 9 a.m.